Welcome to your online pre-calculus lesson. I am Mr. Gongora, and tonight we are going to be talking about section 4.2, Trigonometric Functions and the Unit Circle. So our objectives for this section are to use a unit circle to define trigonometric functions of real numbers, recognize the domain and range of the sine and cosine functions, find exact values for the trigonometric functions at a specific angle, pi over 4, then use even and odd trig functions, recognize the fundamental identities, some periodic properties, and finally to evaluate trigonometric functions with a calculator. All right, so we're going to start by talking a little bit about calculus. Okay, so first thing is the word trigonometry means measurement of triangles. So if we had a right triangle, right, we know that these other two angles have to add up to 90 degrees. So if we're going to start talking about trigonometry using right triangles, the domains of these angles has to be somewhere in between 0 and 90 degrees, right? So the problem with that is that when we talk about problems in calculus, they're solved with functions whose domains are all real numbers. Okay, so instead of starting our discussions with trigonometry with right triangles, we're going to start with something called the unit circle. Okay, and the unit circle is just a circle with a radius of 1. Okay, its center is going to be on the origin of a normal XY coordinate system. The equation of this circle, if we remember our formula for circles, right, was x minus h squared plus y minus k squared is equal to r squared, where h and k are the coordinates of the center of the circle. In this case, it's going to be 0, 0. And the r squared is the radius squared. So in this case, if the radius is 1, 1 squared would be 1. These two are both 0, which is where we get our equation of a unit circle. So our equation is just x squared plus y squared equals 1. Okay. Not terribly important to remember that, but it is good to know where the what the equation of the circle is, just in case you need it. Okay. We can use the formula for the length of the circular arc, s is equal to the radius times theta, to find the length of any intercepted arc. Okay, so s times r is theta. The radius of the unit circle is 1. The radian measure of the central angle is something. It's whatever we want it to be. In this case, the variable would be t. It could be theta. It could be whatever. But because the radius is 1, okay, the length of the intercepted arc is the same as the angle, right? The radian measure of the central angle. That's why the unit circle is so special, okay? In a unit circle, the radian measure of the central angle is equal to the length of the intercepted arc, and both are given by some variable. Mostly we'll use t, some real number t. Okay, that's going to be very, very helpful because it means that interesting stuff happens with the unit circle here. Okay, so let's see what this actually means. If we look at these two figures right here, the radian measure of the angle and the length in the intercepted arc are both shown by t. So this angle right here and this arc are going to be the same number. Let's take a point on the circle, xy. Okay. It is going to be this distance. It's going to be the t away from the starting point. Remember, the starting point of any angle is going to be on the positive x-axis. And if we're on the positive x-axis and the radius is 1, this is going to be 1, 0. This point right here, that's where we're going to start. We're going to travel along the circle to this point right here, this point P. And we're going to move counterclockwise to give us a positive angle, or we're going to move this way to give us a negative angle. But no matter what, as I go around here to all these different points, if I am making an angle starting from here and going around the circle, I'm gonna wind up somewhere on this unit circle, somewhere on this figure, okay? And wherever I stop, whatever angle I decide to stop at, right, there's going to be a point where the line representing the angle intercepts the circle, and the arc length of that angle is also going to be the same as the measure of the angle itself. Okay, and this is true for any real number. For any amount that you spin around this circle, you're going to wind up somewhere on here. You can spin around once, you can spin around backwards, forwards. No matter how many times, you're going to get somewhere on this circle when you stop. Okay. Uh, there are some interesting functions that are going to describe this phenomenon. Um, if we think back for a second, let's take a real easy function, a line. Okay, the input of a line is an x value. The output of this function would be the y coordinate on this line, right? Makes sense. Not too crazy there. Let's take a different function. If we look at the logarithmic function, right, the input is a number, the output is an exponent, okay? It is an exponent that you would raise to and give you this power, okay? So functions don't always have to just be points, right? Inputs could be something and outputs could be something else depending on the definition of the function. Okay, so the reason why I brought that up is as we start to look at trigonometry, we're going to define our 6 special trigonometric functions. The inputs of these functions are going to be real numbers, represented by t, which represents an angle. The output of these functions are going to involve this point, the point on the unit circle where the angle intercepts the circle. Okay, so it's just going to be an xy coordinate somewhere on this unit circle. The trig functions have names that are words, just like logarithm, rather than single letters, like f or g of h, right? So, for example, our first function that we're going to talk about is the sine. And the sine represents the y coordinate of this point, okay? So when we're using the sine function, the input is an angle, the output is the y coordinate of that angle where you stop on the unit circle, okay? The value of y depends on the real number, and it's thus a function of t, right? If this is the input, this is the amount of the angle, okay, then the output is going to be the y coordinate at that angle. Okay. So the expression sine t really means sine of t, where sine is the name of the function t, and a real number is an input, right? I think we just covered that. Okay. The 6 trig functions. Let's skip something. Yeah. Okay. So the 6 trig functions, we abbreviate them. Okay. So we usually use the first 3 letters, except for cosine and cosecant both have the same COS at the beginning. So cosine is the more common one, so cosecant turns into CSC. Okay? This is not the sin function. It's not the cos function. It's not the tan function, right? They're sine, cosine, and tangent. These are just the abbreviations for that particular function. Just like this is not a log function, is a logarithm, but most of the time we just say log. This, right, we don't say ln, right? This is the natural log. So try not to call the sine function a sin, okay? But all of them, we look at their first 3 letters for the abbreviation so that we don't have to write as much when we're using these functions, okay? Sine, cosine, tangent. cosecant, secant, cotangent. That's just the way we're going to write it. Now, each of these has a special relationship with the point P, this point, okay? So, an example, a point P on the unit circle corresponding to a real number is shown in the picture, right? We're going to go this distance, that angle, okay? Here's the point on the circle where that angle stops. This angle, and because this is a unit circle, this arc length are going to be equal to each other. And this point happens to be these two coordinates, right? It's in the third quadrant, so both the x and the y are going to be negative, so I'm going to go left, right? This is 1, right? This is a unit circle, so the radius is always 1. This distance is 1, but I have to go left and down, okay? So this coordinate is negative 3 over 5, negative 4 over 5. If I wanted to say what is the sine of this angle, it would be the y coordinate, negative 4 over 5. The sine function is the y coordinate of P, so this one is negative 4 over 5. Okay, so like we said, is that all these 6 trig functions relate to this point P. It does something with these coordinates, okay? The inputs to all these trig functions are angles. The outputs depend on what the function is. So sine gives you just the y coordinate. Cosine gives you just the x coordinate. The way I like to remember this is that x comes before y, c comes before s. So it's always cosine x sine y because c comes before s. Okay, now the rest of them get a little more involved. The tangent function is the y coordinate divided by the x coordinate. And as soon as you throw a division in there, we know that the denominator cannot be equal to 0 or else the function is undefined. These two functions are never undefined because no matter what the angle is, you're going to be somewhere on the circle, so you're going to get an x coordinate, you're going to get a y coordinate. But for the tangent function, somewhere the denominator is going to be equal to 0. Somewhere, if x is equal to 0, right, on a circle, that would be here and here. Right? X is equal to 0 at those 2 points. So at 2 places on the circle, the tangent is going to be undefined. These are all reciprocals of each other. So the way I like to remember the reciprocal identities is opposites go together. Sine goes with cosecant, cosine goes with secant, opposite letters in the front. Tangent and cotangent sound the same, so they go together. So all you do for the reciprocal identities is take the reciprocal. So instead of y, cosecant is 1 over y. Cosine and secant, secant is 1 over x. Tangent is y over x. Cotangent is x over y. Okay, so because this definition expresses function values in terms of these coordinates on a unit circle, sometimes we call trigonometric functions circular functions. And we talked about that the second ones are the reciprocal functions. Okay, let's actually try to do this. Okay. Now, there are certain places on the circle that are kind of important. We'll get to that in a later section. For now, you know what the point is going to be. So in this figure, t is a real number equaling to the length of the intercepted arc of an angle that measures t radians, and this point, p, is negative 1/2, negative 3 over 2. Both common numbers in trigonometry. And remember, if we're on a unit circle here, all these numbers have to be less than 1. So, you know, expect some sort of fraction for all these answers. Okay, so use the figure to find the values of the trig functions at t. So let's go through them all. The sine, let me write that a little bit better. The cosine, the tangent, and then we'll do the reciprocals, the cosecant, the secant, and the cotangent. Okay, so the most important ones, sine and cosine. Remember, sine is the y coordinate, cosine is the x coordinate. So we just look at the two coordinates. So the sine of this would be radical 3 over 2, the y coordinate. The cosine would be negative 1/2. Now the tangent is going to be y over x. So we're going to take negative radical 3 over 2 over, or sorry, negative radical 3 over 2, the y coordinate, over negative 1/2. To divide a fraction by another fraction, we multiply by the reciprocal. The 2's cancel, and we get negative radical 3. Okay, so those are my first 3 functions. Then to get the reciprocal functions, I just flip them over, remembering, of course, that this is not okay, because we'd never leave a radical in the denominator. So multiply the top and the bottom by the square root of 3, and we get 2 radical 3 over 3. For secant, flipping over 1/2 is easy. We just flip it, 2 over 1. And for cotangent, right, it's going to be 1 over radical 3. So negative 1 over radical 3. Multiply the top and the bottom, and we get radical 3 over 3. Okay, so those are the 6 trigonometric functions at this point. So whatever this angle happens to be, and I actually know it's going to be, no, what is it going to be? Not 2 pi over 3. Actually, when we get to that, you'll recognize these numbers. But I know the coordinate, it's given to me, and eventually I'm going to use the angle to get these 2 coordinates. Okay, but for now, the goal is to just remember what these different trigonometric functions represent in terms of this coordinate. Let's do another one real quick, if I have it. No. Okay. All right, so next, find the values of the trigonometric functions at pi over 2. That point, 90 degrees. Okay. That coordinate is a quadrantal angle. That means that because this is a unit circle, that radius is 1, this is going to be a point 0, 1. Okay, so sine, cosine, tangent, cosecant, secant, and cotangent of t. In this case, t was pi over 2, so I could have actually put the sine of pi over 2, and I should have put that, but I don't want to erase them all. Okay, so the sine of pi over 2 is going to be the y coordinate. The cosine is going to be the x coordinate. The tangent is going to be y divided by x, which you cannot do. So the tangent of pi over 2 is undefined because we take 1 divided by 0 and it doesn't exist. The reciprocal of 1 is still 1. The reciprocal of 0 is undefined. Okay, because this is technically 0 over 1. When we flip it, we get 1 over 0. And the same thing here, cotangent, and we can think about secant as 1 over x. Cotangent, however, is going to be x over y. So 0 over 1, which is 0. Okay? So with functions like this, with quadrantal angles, you're going to get 2 out of the 6 to be undefined. Okay, so you just got to be careful with that. Okay. So let's talk a little bit about domain and range. All right. So the domain and range of each trigonometric function can be found from the unit circle's definition. So if we look at the sine and cosine functions, okay, we'll look at the others later, but if we look only at the sine and cosine functions, the input is an angle, the output is any coordinate, any y coordinate on the circle, okay? So if I think about what am I allowed to plug in for an angle, could they be positives? Yeah, I can turn around the circle in this direction. Could the angles be negative? Yeah, I can turn around the circle in that direction. Whoops. So we have, because t can be any real number, the domain of the sine function is all real numbers, negative infinity to positive infinity. The range, however, and this is true for cosine as well, the range, however, is a y value. Well, the furthest I can go up in this function is 1, because the radius of this circle is 1. The furthest I can go down on this function is negative 1. Okay, it's the y coordinate, so that's why I'm going up and down. All right, but the highest I can get is 1. The lowest I can get is negative 1. Therefore, the range of this function is from negative 1 to positive 1, okay, including negative 1 and positive 1. Okay, so domain, all real numbers, range from negative 1 to positive 1. Okay, same for cosine. Cosine, the domain is still negative infinity to positive infinity. Remember, this is the angle, this is the x coordinate, and the range is still negative 1 to positive 1, but not because it's the highest, because this function, the biggest number I could get as an output is 1. The smallest number I can get as an output is negative 1. Left and right. Seems weird we're thinking about left and right when we're doing a range, but again, these are the outputs of the function. It's the x coordinate of this point. The biggest number I can get is 1. The smallest number I can get is positive 1 because of the definition of this circle, that the radius is 1. Okay. So domain and range of the sine and cosine function, they're both, domain is both negative infinity to positive infinity, and the range of both of these functions is negative 1 to positive 1 inclusive. Okay. Now, let's go to a specific point. Okay. Trig functions at pi over 4 occur frequently. Pi over 4 is 45 degrees. This is a pretty important uh, angle, pretty important triangle, 45, 45, 90 triangle. Okay, so how do we use the unit circle to find the values of a trig function at pi over 4? Okay, first we need to find the coordinates of p on the unit circle that correspond to pi over 4. Okay, and we can do this with a little bit of algebra. Okay, so if we know the equation of the unit circle is x squared plus y squared is equal to 1, right? And I know that that is point AB, okay? So I could say that a squared plus b squared, because that's the x and that's the y coordinate, is equal to 1. Then, because this line y is equal to x goes through this coordinate, right? We know that x and y have to be the same thing. So I could just say, using substitution, that 2a squared is equal to 1, divide out the 2, that a squared is equal to 1/2, take the square root of both sides, and we get that a is equal to 1 over the square root of 2. Really, I don't want to write it like that, of course. So I get that this is the square root of 2 over 2. Okay, so that means that this point right here at pi over 4, that means this angle, which is the measurement we'll talk about the most. It also means this arc length around the edge of the circle, that this point, AB, the 2 points are going to be the same, and they're both going to be radical 2 over 2. Okay. That means that the sine of pi over 4, the cosine of pi over 4 are both going to be the square root of 2 over 2. And the tangent of pi over 4 is going to be the x or the y coordinate, the sine, over the cosine. And if they're both the same, when you divide the same thing by the same thing, you get 1. Okay? These, and let's do the other three, just for fun. The cosecant of pi over 4, the secant of pi over 4, and the cotangent of pi over 4. The reciprocal of 1 is just 1. That's the easy one. Radical 2 over 2. When I flip that over, I go back to that. When I rationalize this again, I now have 2 radical 2 over 2, which goes back to just radical 2. And the cosecant and the secant are the same as well. Okay. These functions, these trig values for pi over 4 are one of the most common. Okay, we're often going to see trig functions evaluated at some multiple of pi over 4. It would be a good idea to memorize these values shown in this box. And when we get to all of them, I'll show you a trick how to memorize these. Because this was 45 degrees, right? This is one of our special angles. There's more. You can't forget 30 and 60. Okay? We'll do that in the next section. But for now, right, if we know these two functions, or if we know the trig value or the coordinate value of the angle pi over 4, I can start building my full unit circle. Okay, so let's start this and let's fill in all these places with degrees, radians, and coordinate values. We're going to get rid of these for now. We'll come back to those later, but we can fill out everything else right now. Okay, let's start with degrees. 0. I like to go by 30s. 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, and 0 and 360 degrees all the way around. Then I like to do the 45 degrees. 45, 90, 135, 180. We were just adding 30 degrees, and now we're just adding 45 degrees to get to 180, 225, plus 45 gives me 270, and 315. So that takes care of all these special angles in degrees on my unit circle. Next, we have to do radians. So I do the same thing again. I start with pi over 6. 30 degrees and pi over 6 are the same. So I'm just going to use this as a handy pi over 6. And then I just keep, just like I added 30 each time, I'm going to add pi over 6 each time and make sure that I reduce. So this would be 2 pi over 6, which reduces. 3 over 6, 3 pi over 6, which reduces. 2 pi over 3, so that's 1, 2, 3, that's 4 pi over 6. 5 pi over 6, 6 over 6 reduces to pi. 7 pi over 6, 8 pi over 6 reduces to 4 pi over 3. And then this would be 3 pi over 2, 5 pi over 3, and then that would be 11 pi over 6, because that one does not reduce. Now, and of course, right, this is 0 and 2 pi in radians. That doesn't look like a 2 pi. So now I go by 45 degrees. Pi over 4. 1, 2 pi over 4 is pi over 2. 3 pi over 4. 4 over 4. 5 pi over 4. 6 and 7. So now we have successfully labeled every angle that is special in my unit circle. Now let's do the coordinates. Let's start with the easy ones, the quadrantal angles. This is a unit circle. The radius is 1. That means you go right 1 and up nothing. That means you go left 1, up nothing. And I'll just put the parentheses here so we can see it. This point would be left x0, up 1. This point would be 0, negative 1. Okay, so those are the easier ones. And now, based on what we just did, that the sine and the cosine, the x and the y coordinate at 45 degrees at pi over 4 are going to be the same number, and they're going to be the square root of 2 over 2, square root of 2 over 2. This is quadrant 1. The x coordinate, this is the center of the circle. The x coordinate and the y coordinate in quadrant 1 are both positive. In quadrant 2, x is negative, y is positive. In quadrant 3, they're both negative. This is not something that should be terribly new. In quadrant 4, x is positive, y is negative. Okay? We'll come back to the other 8 angles in the next section. But we now have almost completely finished making a basic unit circle. Okay? And again, these coordinates are going to be the sine and the cosine value, sine, cosine, for this particular angle. Okay. Let's start talking about some other identities. All right. So we have some definitions, even and odd. Even functions, it functions even when you plug in a negative number and you go back to where you started if f of negative t is the same as f of t. And it's odd if f of negative t is equal to negative f of t. So think about what a negative number actually means here. It means that our angle is negative. So P would be our positive angle, and Q would be our negative angle, both with the same arc length. Okay? So P would be xy, cosine sine, and Q would be cosine of negative t, sine of negative t. Notice that the x values are the same, but the y values, P is positive and Q is negative. So that means that the cosine of negative t is equal to the cosine of t, and thus it is an even function. The sine of negative t is equal to the opposite of the sine of t, right? This had a positive y coordinate, this has a negative y coordinate, and it's the same coordinate, it's the same distance up and down, okay? So that means that the sine of negative t is equal to the negative sine of t, which makes it an odd function. And it doesn't matter the length of the angle, okay? No matter what. Right? If you spin all the way to here, right, and then you spin backwards over to here, right, it still has the same x coordinate, both negative, doesn't matter, but opposite y coordinates. Okay, so this is going to be the same no matter what. And we can extend this definition to the other functions as well. So the cosine and its reciprocal function are the only two that are even. All the rest are odd. Sine and its reciprocal, tangent and its reciprocal. Okay? And basically these ideas of even and odd and some stuff that we'll get to in further sections called reference angles, these ideas are going to help us boil everything down to somewhere on this basic circle, okay? And you can see that, you know, x coordinates the same here, and opposite y coordinates. Okay, so what can we do with this? So find the value of each trigonometric function. So instead of worrying about a negative angle, right, because that can get a little bit confusing, it's easier to say, well, hey, the cosine is even, so I know that these two are going to be the same, and that the cosine of pi over 4, which we just figured out, is radical 2 over 2. Okay? Again, I was able to get rid of this negative because of this identity that says these two are the same. Okay? And then in the second one here, the tangent, I know that the tangent is odd. So I can calculate the tangent of positive pi over 4 and then just make the answer negative. So the tangent of positive pi over 4 is 1, which makes this negative 1. Or if you wanted to, you could have just used a negative angle, but I think that it's a little bit easier to remember just the basic functions on a basic unit circle of the positive angles as opposed to negative angles. Okay, so as we go through this chapter, we're going to use a lot of these relationships to help us with calculating values, graphing these things later. But one of the most common relationships are called the fundamental identities, and each one with its reciprocal identity and its quotient identity. We'll get to in a second. But these identities are equations that are true for all real numbers for which the trigonometric expressions in the equation are defined. So cosine is defined for everything, but secant is not defined at when x is equal to 0. So you just got to be careful about that. If we start with cosine, and we just know that because cosine is equal to x and secant is equal to 1 over x, I can just replace cosine with x because they are equal to each other, cosine of t, right? And so this idea gives us our 6 reciprocal identities. That sine is 1 over the cosecant. Cosecant is 1 over the sine. Cosine, 1 over the secant. Secant, 1 over the cosine. Tangent, 1 over the cotangent. And cotangent, 1 over the tangent. Okay? Again, these are just switching, right? These are the ones that go with, right? I said sine and cosecant were reciprocals before. Now this is the reciprocal identity, just replacing the point with another function. These come in extremely useful, not so much in this chapter, more in the next chapter when we start doing proofs with these. There's 2 other relationships that follow this called the quotient identities, that the tangent is equal to the sine over the cosine, and the cotangent of t is equal to the cosine of t over the sine of t. Okay? There always has to be, I know I've been saying sine and cosine, but you always have to have some sort of input, some sort of angle in these functions. Okay, so what can we do with this? All right. If I know that the sine is 2 over 5 and the cosine is radical 21 over 5, I can find the value of all of the other ones. Okay, so let's get all 6. The sine of t, the cosine of t, the tangent of t, the cosecant, the secant, and the cotangent. Sine is given to me. Cosine is also given to me. Tangent is equal to the sine over the cosine. And technically, this is the x-coordinate and this is the y-coordinate, so I can think about it like that as well. So I just have to put the sine. So that's 2 over 5 over the square root of 21 over 5 multiplied by the reciprocal. So those cancel. So we get 2 over the square root of 21, which we don't like. So we're going to rationalize that to give me 2 square root 21 over 21. Not pretty numbers, but it's okay. And we'll see that this should make a lot of sense when we start doing the next section and thinking about this in terms of a right triangle. Cosecant, flip the sign over. Secant, flip the cosine over, but don't leave it like that. So we get, well, we'll just do this out. So multiply. So we get 5 square root 21 over 21. And you could flip this over and re-rationalize it again, or you could just look back to our earlier work right there and flip that one over before we rationalized it. So this becomes the square root of 21 over 2. Okay, so if you know the sine and the cosine, okay, we can get all the other ones. In fact, if you know any two, you can get all the other ones. And later on, we'll figure out how to get even more information from this. Okay. There's some other relationships that allow us to work with these functions a little bit more. Okay. So one of them comes from the basic equation of a circle. Remember way back in the beginning, we said that the equation of this circle was x squared plus y squared equals 1. And because we now know that these two are related, we now have this identity, that the cosine squared plus the cosine of t squared plus the sine of t squared is equal to 1. Now, we have a little notation thing here. We can eliminate the parentheses, because this is a lot of parentheses. We got these parentheses, we got these parentheses. Right? We're going to be using a lot of trig functions, and we just don't want to have to write all these parentheses all the time when we want to square stuff, because we're going to be squaring a lot of stuff. So instead of writing this, we're going to rewrite it as cosine squared of t. Means the same thing. Okay, so that you're not squaring the cosine and leaving this angle out, right? It is the entire number, the entire value of that function squared. This is just a trick that we use to save us some confusing parentheses, okay? So we're just going to write cosine squared t plus sine squared of t is equal to 1, okay? Means exactly the same as we did before. This identity appears, we usually write sine plus cosine. These identities are called the Pythagorean identities, and there are 3 of them. The one we'll use the most is this one, that the sine squared plus the cosine squared is equal to 1. Also, tangent and secant go together, cotangent and cosecant go together. So again, I try to remember these with the different letters. I remember that cosine and cosecant go together in the Pythagorean identity because they have the same letter. This one is something that we should just kind of use enough that we just kind of know it. And these are the most common trig functions anyway. So the common ones go together, and then cotangent and cosecant go together, and these are the only 2 that are left, tangent and secant. A little backwards here, where sine and cosine are both on the same side. This is 1 plus tangent, and 1 plus cotangent equals my reciprocal identity. So, again, given that the sine is 3 over 5, and what does this mean? The angle is between 0 and pi over 2. That means it's in the first quadrant. That means the sine is positive as well as the cosine. Okay? Find the value of the cosine using a trigonometric identity. Well, we know that, well, let's write it the right way. So that the sine squared plus the cosine squared of any angle is equal to 1. So that means that 3 over 5 squared plus the cosine squared is going to be equal to 1. 3 over 5 squared is 9 over 25 plus the cosine squared is going to be equal to 1. Subtract both sides. So the cosine squared of t is going to be equal to 16 over 25. I take the square root of both sides, and you get that the cosine, the cosine of t is going to be equal to, now when you take the both sides, when you take the square root of both sides in an equation, you do get a plus or minus, but that's where this comes in. That piece of information right there told me that this answer must be positive, okay? Because it's in the first quadrant. And the x coordinate and the y coordinate in the first quadrant must be positive. Okay, so my answer would be 4 over 5. All right, so periodic functions. Certain patterns in nature repeat again and again. For example, ocean level, tides, goes up, goes back down, goes back up, goes back down. Happens about every 12 hours. So if low tide occurs at noon, high tide will be 6, and then low tide again at midnight. So the entire cycle, to go back to where you started, takes about 12 hours. This would be how I could represent that relationship. That this function at t plus 12 is equal to the original function, right? Because at 12 hours, I'm going to go back to where I started. That is the definition of a periodic function, okay? The period is how long it takes to complete one full cycle. That's important. Period is how long it takes to complete one full cycle, okay? So a function is periodic if there exists a positive number that you could add to your function to make it go back to where you started. And if you think about trigonometric functions, are they periodic? Well, if you start here on the unit circle and you spin around, are you back to where you started? Yes. Okay. So if we begin at any point P, any point on the unit circle, and go around 2 pi, we're going back to the same point. Okay. Because of this, the sine and cosine are periodic. They all have a period of 2 pi. So the sine of any angle plus 2 pi is equal to the sine of just the angle, okay? And that was called coterminal angles, okay? So sine and cosine function have a period of 2 pi, as well as their reciprocals, cosecant and secant. Tangent, however, is a little weird. So like the sine and cosine, the secant and cosecant have 2 pi. Tangent and cotangent have a smaller period because remember what tangent is equal to. It's equal to y over x. So if I have negative y over negative x, that is also the same number as y over x. So if we think about what happened in quadrant 1, we have this point xy. The sine would just be the y coordinate, so it wouldn't be that same y coordinate, right? It wouldn't be the same, this whole point wouldn't be the same until we got all the way back, both x and y being positive. However, the tangent is this one divided by this one. So here it's positive as well as here. So that means that the tangent repeats itself every pi unit, right? 180 degrees. Okay? The tangent repeats itself every pi units, which makes the period of the tangent and the cotangent function pi instead of pi over 2. Okay, so what does this let us do? Okay, so it lets us now find the sine and the cosine and the tangent of numbers like this, numbers that are bigger than 2 pi. So the sine of 9 pi over 4 is the same thing as the sine of pi over 4, yeah, plus 2 pi, which means that the sine of 9 pi over 4 is the same as the sine of pi over 4. And luckily, I know what that is. It's the square root of 2 over 2. A positive 2 over 2, because it's in the first quadrant. Why do we have to do all that? You know, it's better just to remember basic angles as opposed to angles that are getting bigger and bigger and bigger. Okay? But usually what I want to do is I want to use some identity, either this identity, the periodic identity, which is where coterminal angles come from, or an even odd identity to get these to be positive numbers in between 0 and 2 pi. So that way I don't have to go memorizing a ton of different trig functions for all different angles. I'm only going to remember the ones that are in between 0 and 2 pi. So this one, if we remember that it is an odd function, I change this to the negative tangent of 5 pi over 4. 5 pi over 4 happens to break down to pi over 4 plus another pi, which means that this one can just go away, because no matter what I do when I add pi, I'm always going back to the same answer. So the tangent of 5 pi over 4, or sorry, the tangent of negative 5 pi over 4 is the same as the negative tangent of pi over 4. The tangent of pi over 4 is 1. Make it negative to give me negative 1. Okay, so trig functions model this phenomena and repeats indefinitely, right? You can spin around a unit circle as many times as you want. Okay, so 2 pi, 4 pi, 6 pi. We're always going to go around and around and around and around and around. Okay, so you always want to get a number in between 0 and 2 pi for sines and cosines and secants and cosecants to evaluate them. You always want a number somewhere in between 0 and pi for a tangent and cotangent. Okay, that's pretty much all that says there. And this repetitive behavior works for any number that I want to plug in there, positive or negative numbers. So I can add 2 pi, I can subtract 2 pi, the cosine and the sines are always going to be the same, and tangent, I could add pi or subtract pi, and it's always going to go back to the regular tangent. All right, last thing, calculator. Okay, so we use this unit circle to find values of trig functions at pi over 4, because these are common. These are exact values, right? The square root of 2 over 2. I don't evaluate that. I use the exact value. You can find approximate values for trig functions by using a calculator. So you got to be careful with this, because if you're going to use a calculator to calculate trig functions, it has to be in the right mode, either degrees or radians. Most of the time, we're going to want it in this when we're dealing with a circle. When we're dealing with triangles or with word problems, we're going to use mostly degrees. So you're going to have to be comfortable enough. You can't just put it in one and then forget about it. You're going to have to be comfortable enough to take your calculator back and forth. If you're not, look it up on YouTube, figure out or find the manual for your calculator and figure out how to go between degrees and radians. Mostly any calculator that has a sine, cosine, and tangent button on it can go between degrees and radians. You're just going to figure out how to do it. Sine, cosine, tangent button. Depending on the way your calculator works, your button presses are going to be a little bit weird. I don't think I've ever seen a calculator that actually does cosecants, secants, and tangents, actually has a button for that, but all calculators pretty much have that button, the reciprocal button, okay, or looks like that on some calculators. So if you want to find the secant of pi over 12, find the cosine of pi over 12 and take the reciprocal. Okay. If you want to find the cosecant of something, take the sine and take the reciprocal. Right. Press this button after you're done. Okay. And that'll give you this idea. Right. Just be careful that you're inputting this the right way. Scientific calculators, graphing calculators is going to be a little bit different. The button press thing that you the order that you press the buttons in is going to be a little bit different. So just experiment with your calculator a little bit. You might actually want to practice this and see if you can get that the secant of pi over 12 is equal to 1.0 or 1.0353. All right, let's do a couple things on your calculator. So I already know that the cosine of pi over 4 is, whoops, I already know that the cosine of pi over 4 is radical 2 over 2. That's not the point of this. The point is to, I have to change the mode on my calculator. The point is to see if you can get the correct decimal. So, using your calculator, and if your calculator is pretty good, it might actually spit this out. It might actually spit out radical 2 over 2. That's great, because then you're going to be getting exact answers. But that's not what I want. I want to find the decimal answer, and you should get 0.7071. Okay. This is not a common angle, so I don't happen to know the cotangent of 1.2 radian. These are radians. That's a radian. There's no degree sign. That's a radian. There's no degree sign. We're mostly going to be using radians when we're talking about circles. Unless you see a degree sign, always assume it's a radian, unitless measurement. So here, we're going to have to do this. We're going to have to find the tangent of 1.2 and then flip it over. So the tangent of 1.2 would be 2.572. And so then I just put that on the bottom of a fraction, either with the reciprocal button, or you can just do it manually, and you get 0.388 877, right? 3.8877 round up, 4 decimal points is plenty. So the point of these questions is just to make sure that you know how to use your calculator and that you are comfortable going between the different functions on your calculator and flipping back between degrees and radians. So that is the end of this section, 4.2, trigonometric functions and the unit circle. Again, a lot covered in these sections, so definitely recommend breaking this up into small pieces.